A $35 computer, no internet connection, no API keys, no cloud subscription, and it's controlling physical hardware by having a conversation with an AI. That's not a concept demo. That's a working GitHub project you can clone today. Here's what's actually happening. Someone took a Raspberry Pi 4, the little single board computer you can hold in your palm, and ran a local large language model directly on it using Ollama. Then, they connected that model to the Pi's GPIO pins, the physical hardware interface, through something called tool calling. You type a message like, turn on the LED, and the model doesn't just reply with text. It executes a function. The LED turns on. No middleman, no server in Virginia, no monthly bill. Let's be concrete about what tool calling means here, because it matters. Modern LLMs can be given a list of functions, tools, and when the model decides one of those tools is relevant to your input, it outputs a structured call to that function instead of plain text. In software, you use this to let an AI search the web or query a database. On a Raspberry Pi, those tools are things like setting a GPIO pin high or low, reading a sensor, triggering a relay. The model becomes the brain. The Pi's hardware becomes the hands. The project uses Ollama to run the model locally, models like Llama 3 or Mistral, depending on what fits in your RAM, and a Python layer that bridges the model's tool calls to the actual RPI GPIO library. You describe what hardware functions are available, the model learns to call them, and you get an AI-controlled hardware interface that runs entirely on your desk. I ran through the setup. It takes maybe 20 minutes if you already have Ollama installed. The repo is clean. There's a clear example with an LED. The tool definitions are written in plain Python dictionaries, so extending it to your own hardware is straightforward. This is not a proof of concept buried in 3,000 lines of abstraction. It's readable. But here's the thing, and this is where honesty matters more than enthusiasm. The Raspberry Pi 4 is not a fast inference machine. We're talking about response times measured in tens of seconds, sometimes more, depending on the model you load and the quantization level. For a demo, that's fine. For anything real-time, robotics that needs to react in under a second, industrial control, anything safety critical, this hardware gap is a wall, not a speed bump. The Pi 4 has 4 to 8 gigabytes of RAM, and no dedicated GPU. Running a 7 billion parameter model on it is pushing the hardware to its absolute ceiling. What surprised me was how well the tool calling actually works within those constraints. The model reliably produces valid JSON function calls for simple commands. It doesn't hallucinate tool names, it wasn't given. The Python bridge catches malformed outputs gracefully. For the scope it targets, it's solid. But there are real gaps. The current project covers GPIO control, pins, LEDs, basic digital outputs. It doesn't include I2C sensors, PWM motor control, camera integration, or anything that requires streaming data back to the model in a feedback loop. The model acts on your instructions, but it's not observing the physical world in return. It can turn a light on. It can't tell you if the light is actually on. That's a one-way channel, not an agent. Error handling is also minimal in the current implementation. If the model produces a tool call with an out-of-range pin number, you'll want to add your own validation layer before this goes anywhere near real hardware. The repo itself notes this is experimental. Take that seriously. Now, where does this realistically go? The most credible near-future version of this is in home automation prototyping. Not replacing Home Assistant, but letting hobbyists build custom logic in natural language instead of writing automation scripts. Imagine telling your Pi, if the temperature sensor reads above 28 degrees, turn on the fan relay. And that just working, without you writing a single conditional. That's achievable on this foundation with a feedback sensor loop and a slightly more capable model. The other plausible direction is education. Teaching embedded systems is hard because the barrier between software logic and physical results is abstract. A local LLM that translates intent to hardware action, live on the desk, is a genuinely interesting teaching tool. No cloud dependency means it works in a school with no reliable internet. That's not nothing. If Raspberry Pi 5 or the upcoming Pi hardware iterations close the inference gap, and they are, generation by generation, this architecture becomes significantly more practical. The software layer is already there. It's waiting for the hardware to catch up. So why does this project exist? Because there's a real and growing frustration in the maker and embedded community with AI tooling that requires a cloud dependency for everything. Every interesting AI feature in hardware projects assumes you have a reliable internet connection, an API key that costs money, and a server you don't control holding your data. For hobbyists, For researchers in low connectivity environments, for anyone building something that needs to work offline, that assumption is a deal breaker. This project is an existence proof. It says the pieces are already here. Ollama runs locally. Tool calling is a standard capability. GPIO control is a solved problem. Someone just had to connect them, and now they have. If you're building something on this, extend the tool library, add sensor feedback, try it on a Pi 5. The GitHub link is in the description. Next episode, we're looking at another offline first AI project, this one running vision models on edge hardware. If that sounds relevant to what you're building, subscribe so you don't miss it.